I think we should start the afternoon session. So the first speaker of this afternoon is going to be Christoph Federrath, talking about the star formation rate in molecular clouds.
Is this working? Yep. Okay. Yes. So I would like to start this talk by thanking the organizers for bringing PP6 here to Heidelberg, which is actually the place where I did my PhD. And it's great to be back. And it's even greater, actually, to see that so many people are here who are interested in star and planet formation. So let me start by introducing the team. Here, led by Paolo Padoan and myself, Gilles Chabrier, Neil Evans, Jens Jorgensen, Doug Johnston, Chris McKee, and Arke Nordlund. All of them are here in the audience today. And, well, the basic idea, or the basic thing I want to talk about is the star formation rate and how we can get a star formation rate from the statistics of supersonic turbulence. That's really the main point of the talk, and it's a very simple one. There's a connection between the rate of star formation and supersonic magnetized turbulence. And we are actually now at a stage where we can start to get theoretical estimates of the star formation rate, or actually a predictive theory of the star formation rate that can be compared with numerical simulation, which I will show, and that can eventually, of course, also be compared with observation in the Milky Way. Okay, so let me start with the basic problem. So here's the problem. Two clouds, this is the Pipe Nebula and Rho Ophiuchus, and even though they are similar in column density, they have and in mass, they have a very different star formation rate. And it's a real challenge to explain why the star formation rate is so much different. It can't just be the column density that determines the star formation rate. There must be other parameters. And I will argue that it's the parameters of the turbulence that determine the star formation rate. Here's another way of looking at this. You all know there's a relation between the star formation rate column density and the gas column density, and this is essentially the Kennicutt-Schmidt type relation here. But when we add clouds from our own galaxy, from the Milky Way, we see that they are significantly offset from this extragalactic relation. So there's first of all a desire, of course, to understand where this relation comes from. Then why is there an offset, and why is there such a huge scatter? So for any given gas column density, there's 2 orders of magnitude in star formation rate column density. And we somehow have to understand why this is the case. But let me start first with summarizing a few of the local processes that influence star formation. And those are radiation, ionization, winds, sort of one thing, and then magnetic fields and outflows and jets. And even though, of course, these physical processes all have their specific properties and they need to be investigated in much detail to understand them, the overall effect of this on the star formation rate and the star formation efficiency is that it leads to a core-to-star efficiency of about 50%, or something between 30 and 70%. So in other words, of course, not all the mass of a core falls onto the protostar. There's always some ejection of matter, which is essentially boils down to a core-to-star efficiency of about 50%. And we've already seen this plot in the previous talk. This is just another way of saying that maybe there is, because the dense core mass function is so similar to the IMF, there's just a shift with this kind of efficiency here. So let me go through these processes: radiation, magnetic fields, and outflows. And first, radiation. And I would say this is primarily important on relatively small scales and at relatively high densities. And here's a nice example of a simulation by Offner et al. You can see this is about 0.6 parsec. Here's a simulation with radiation, hydrodynamics, and here's one without. This is a control run, and this is the temperature in the radiation run. And you clearly see that the temperature rises in these core regions, but otherwise it's confined to relatively small scales, about the size of cores, 0.1 parsec, as Philippe André was telling us about. Here's the temperature versus density, and you can see that essentially for a quite large range of densities, the temperature is somewhere between 10 and 20 Kelvin, and only at about 10 to the 8, 10 to the 9 particles per cubic centimeter, temperature starts rising. Magnetic fields. This is an interesting example here by Myers et al. Recently, where they compare a run with magnetic field with radiation, with magnetic field without radiation, so isothermal, and then one without a magnetic field and radiation. And what I find particularly interesting about this simulation is that it seems that the effect of radiation is actually not as strong as the effect of the magnetic field, which you can see when you compare these two magnetic field runs. It doesn't matter so much that this is isothermal compared to radiation. The overall structures are very similar, whereas here you have still a lot of fragmentation. So magnetic fields essentially reduce fragmentation. That's one thing, but then we also know, of course, on smaller scales, that magnetic fields influence the accretion disks. Magnetorotational instability is important for planet formation, but also they drive jets and outflows, because when the core contracts and rotates, the magnetic field gets wound up in the disk, and eventually this is like a spring that releases a bipolar outflow in both directions, which has been, of course, observed, but also has been shown in adaptive mesh refinement simulations for some time, and more recently also with smooth particle magnetohydrodynamics. Now these jets have essentially two effects. There's one direct effect, so it reduces the star mass, as I said, because mass is expelled from the core, and the other one is more indirect, because this drives motions. Of course, it might drive turbulence, might further reduce the star mass, but also maybe trigger star formation. And so, as I said, the overall effect is that it leads to a core-to-star efficiency of about 50%. Here's another nice example from Ginsburg et al. There's a poster actually here showing these bullets that are being thrown out, which is really like an explosive kind of feedback mechanism that's going on here, which may also be capable of driving turbulence. Okay, so we have to think about what things can drive turbulence. And there are various possibilities. Here is a beautiful picture of the Carina Nebula. And you see these ionization fronts here. There's old clusters that maybe drive these. They blow these bubbles, and then we have these protostellar jets and outflows. And actually, when you zoom into one of these regions here, you see this nice jet that's also on the Protostars Planets poster. And here, of course, I would like to point out that these things are a little bit like needles that go into the gas. It's a bit unlikely that these jets really drive the large-scale structure that we see in the whole cloud. But they certainly contribute to driving turbulence on small scales. We need other processes. And one of the things favored in this review are supernova explosions. But there's also an effect from the galaxy itself, creating shear, and when a molecular cloud, not a molecular, actually a H1 cloud, passes through a spiral arm, becomes molecular, it gets compressed and squeezed in this spiral shock, and then eventually gas falls into the potential well, which also stirs up the gas. So there are many processes that can drive turbulence. And I want to go a bit further on telling you about turbulence, because we have heard in the last 3 talks the word turbulence a couple of times, and also turbulence is important on small scales in accretion disk for grain growth and for the magnetorotational instability. So I just want to put this into a larger context here. Turbulence is essentially, well, Leonardo da Vinci already drew this, water flowing into a tank and having these large eddies that break up into smaller and smaller structures, which he drew here. And this is essentially what is called a cascade. So these large structures break up into smaller ones from large to small scales, where eventually the energy is dissipated into heat. And so there is a heuristic model by Kolmogorov that says this power law here of kinetic energy as a function of wave number or scale goes with k to the minus 5/3, which in other words says that the velocity of these eddies scales with their size to the 1/3 power. The problem is that this is not observed in molecular clouds, and the simple reason is that molecular clouds are not like this, incompressible. They are highly compressible. And so that leads to the Larsen relation, which actually shows that the exponent of the velocity-size relation is closer to 1/2, which can actually also be seen in numerical simulations. So the spectrum that you would expect is k to the minus 2, and when you compensate for that k by multiplying by k squared, you see a relatively flat spectrum, which also converges with resolution. So the important thing is that turbulence in the ISM on large scales is highly supersonic, or in molecular clouds, and eventually we have to revise this picture that I showed you before. So we certainly have some important scale called the sonic scale, where the turbulence becomes subsonic. So there's essentially two regimes, one regime which is shock dominated, where the Mach number is larger than 1, and a regime where it's subsonic, which is described by Kolmogorov turbulence. And molecular clouds basically live here, and protostellar cores are here. So the sonic scale is really an extremely important scale for setting the fragmentation, but also setting properties of star formation. As we will see later, we need the sonic scale to predict a star formation rate, and eventually then that's us. All right, so coming back to all these drivers, of course, if you think about ionization fronts and bubbles, they go woof, supernova explosion, woof, gravitational infall, galactic shocks. So this all compresses the gas, essentially. And that's how complicated reality is. But what we do when we try to model these things in a computer is this. We take a box. We put some gas in the box, we shake the box with some sort of forcing term. Of course, ideally, we would like to model all these processes in detail in a huge simulation where we have a galaxy that forms, and this galaxy forms molecular clouds, and these molecular clouds then form cores, which can then drive jets, but we are not there yet. First of all, the resolution that would require is enormous, and of course also the physics. But we all work in different areas here, and we have to talk to each other and combine these things eventually, because we are soon reaching a stage where supercomputers can actually bridge the gap between these large scales. But for the time being, what we can do is just ignore the characteristics, the specific characteristics of these drivers, and do a numerical experiment, a very simple thing. We just say, okay, let's not talk about these in particular, but let's consider how much compression they induce, or how much rotation they induce. And for this, there comes in this experiment called Turbulence in a Box, which has been done by many people. It's not just me. We should be blamed here for this. It has periodic boundaries, and the good thing is we have full control over certain parameters of the turbulence, like the Mach number and the forcing. What has been done in the past is to use this many times, which is the mixer, or in technical terms, a divergence-free force field to drive the turbulence. But of course, you can also do the other extreme, where the curl of the force is 0. So in other words, reality is almost certainly in between these two extreme cases. And this is not to mimic any specific driver, but just to investigate systematically what is the effect of compression compared to rotation. And when we do this in a numerical simulation, comparing these two extreme cases of driving the turbulence, you see that they all create filamentary structures, blobs. But obviously, the voids here of low density gas are much larger, and the density enhancements are much stronger in this case, which can also be more quantitatively evaluated by looking at the fractal dimension, which is actually quite comparable here with 2.3 to observations by Romain Duval et al., for example, whereas this one is more volume filling. So it has a fractal dimension closer to 3, which would be volume filling. Okay, we can, of course, look at this more quantitatively and make a histogram of all the pixels in the simulation, of all the densities that we have. This is the simplest thing you can do, which is called a density PDF. So we plot here the number of pixels with a given density, in particular here in this quantity S, which is the logarithm of the density contrast, density divided by mean density. And this develops a Gaussian distribution. But when we look at these two simulations that I just showed you, then they have a very different PDF. They are both roughly log normal, but the standard deviation is significantly shallower here compared to the compressive driving case. And so that means that the standard deviation that comes in here is not only a function of Mach numbers, or of how much you compress the gas by having a much higher Mach number, but also of how you drive the turbulence. This opens a potential way of learning something about real drivers of the turbulence by measuring this parameter B. If we could do that, we might learn something about the mixture of solenoidal to compressive driving. And in fact, when we look at observations, we see that the PDF of density is indeed roughly log normal. And these are observations actually by Goodman et al. In the Perseus molecular cloud. And when we look more closely at these two regions in Perseus, the shell and NGC 1333, they have relatively similar Mach numbers, but the PDF here is significantly wider than it is here. So in other words, even though the Mach number is here even slightly higher, you would expect a larger PDF or a larger dispersion, but it doesn't have that large dispersion. So there must be a difference here in B between these two regions. This is, of course, just very qualitative. We have to make this more quantitative. But this is difficult because column density is not volume density. And the theory we have is for volume density. So we have to have some conversion from column density to volume density. And there are some ideas how you can do this. And when we plot this function here, tested with numerical simulations, they actually fit quite well when you drive them solenoidally. There's also more data points than this from a different study by Konstantin et al. Showing that this also works. Then this opens up a wedge where the observations that were available at that time actually are in between, and they would be consistent here with some mixed forcing in between those two extremes. Of course, these are only two regions, and in principle, other clouds could actually fill this with different values of B. And there's a more recent study by Kainulainen et al., also using the PDF, but in this case, the integral over the high density tail of the PDF, which they call the dense gas mass fraction, as a function of column density. And there's an interesting and very systematic effect when we go from starless nearby clouds to star-forming nearby clouds and to infrared dark clouds, which are more massive and more distant. One can compare this slope here, or this change in the slope, with numerical simulations that vary this forcing parameter B. And it looks like the starless ones would have very low B. The nearby star-forming ones, so the red sample here, is consistent with solenoidal and mixed driving. But the more massive infrared dark clouds, they actually approach a regime where B could be even higher. And I would like to emphasize that these infrared dark clouds in the sample here by Kainulainen and al. Are not the most massive clouds that there are. There are 5 × 10⁶ solar mass clouds in our galaxy and potentially even more massive ones in other galaxies. Okay, why have I talked all this time about PDF? It's so boring, but the density PDF is really the key for the star formation rate, and not only that, it's also the key ingredient for other theories of star formation, namely the IMF, the star formation efficiency, the Kankar-Schmidt relations. But I want to focus on this, and what they all have in common is that they use an integral over the density PDF from some critical density to estimate the mass above that density, which is expected to form stars or contribute to star formation. And so to build a model or a theory for the star formation rate, we have to have, of course, some mass divided by some time to have the right units here. And to get this mass fraction again, this is just an integral over the PDF, weighted by the density contrast. And then we have to divide by a time, and the natural time for this is the freefall time, of course. And I really want to emphasize here that this freefall time factor is inside of the integral. Previous theories have pulled this out and made it constant, but different densities have different freefall times, and so the contribution of different or the freefall time at different densities has to be weighted properly in this integral. So this factor must be inside of the integral. Okay, and eventually we just put in everything we know, the PDF, we know the definition of the logarithmic density, we know the freefall time. This integral is easy to solve and depends essentially on the width of the PDF, or the standard deviation, and its critical density, which I haven't actually talked about what it is, but the critical density can be, you can come up with a model for the critical density by comparing the sonic scale and the gene scale. And this leads to a dependence of this critical density here on the virial parameter and the Mach number. Well, and the other parameter, so the standard deviation, is already given by this expression here with the forcing parameter and also the Mach number. So if we put this all together, then we have a star formation rate that depends on three basic dimensionless parameters: the virial parameter, the forcing, and the Mach number. And I should also say here that, of course, this is a dimensionless quantity because we have expressed everything in fractions or compared to mean values. If you want to get out a real star formation rate from this, it's easy. You just have to multiply by the actual mass of the cloud and divide by the freefall time at the mean density of that cloud. Then you get a star formation rate in solar mass per year, as you are used to. And then this epsilon here is simply the core to star efficiency, which we, for the time being, assume is about 1/2. Okay, so this is, of course, a function that depends on three parameters. And so to plot this, I just focus here first on a fixed value of the B parameter. So for purely solenoidal forcing, that would be 1/3, and then we can look at the dependencies in the theory. So there's a star formation rate as a function of virial parameter and Mach number. And let's first focus on the dependence on the virial parameter. Virial parameter is simply the ratio of kinetic to gravitational energy. And so if you increase that, eventually your clouds become unbound, which means they must essentially have a very low star formation rate at the end. And this is actually reproduced here. For any given Mach number, these contours fall with increasing virial parameter. And this is seen also in numerical simulations, where Padoan et al. Have increased the virial parameter here using very similar, otherwise very similar numbers here. And you can see that there's a clearly exponential decrease in the star formation rate when you increase the virial parameter. Coming back to this freefall time and the Mach number dependence. When we include the freefall time factor here, as has been proposed by Hannibal and Chabrier, then we get actually a very different dependence on Mach number compared to the original model by Krumholtz and McKee, which did not have this freefall time factor inside the integral. And so this is relatively weak dependence on Mach number, whereas if you add this, you get a strong dependence. And the strong dependence on Mach number does make sense, because as you have higher Mach numbers, you compress the gas more, you have more gas at high densities with very low or very fast freefall times, and so the contribution the star formation rate just becomes larger as you compress the gas more, which is just natural. Now, finally, I want to focus on the dependence of this parameter on this parameter. So I can simply compare the two extreme cases here by switching back and forth between these extremes. And you see when you increase B, so when you compress again the gas more, the star formation rate becomes higher overall. Of course, we would like to test this theory now in detail with numerical simulations. ideally the whole parameter range, but this is very expensive. So I will first focus on one particular case where the virial parameter is about unity and the Mach number is about 10, which is just a typical molecular cloud, and compare two simulations that have these extreme cases, compressive driving, solenoidal driving, and we've seen in Mark's talk that this is a reasonable average value of the virial parameter. And so let's see what happens. Mark already showed this one. And with compressive driving, we see that we again form these much stronger filamentary structures, and they all form cores very quickly. These zinc particles here, they do not represent stars. They are just dense, self-gravitating and bound cores. That's how we model them. But as you see, it takes a significantly shorter time to wind up about 20% or so of the mass in stars in this case than it does here. So this is still running. And so this has a relatively low star formation rate compared to that one. And more quantitatively, the difference here is more than a factor of 10. So the forcing, even though we keep everything else fixed, has an extremely important effect on the star formation rate. And when we compare this with the theoretical prediction, we see that the agreement is actually quite good here. It's not as good here, but given that there's a difference by more than an order of magnitude, they agree quite well. Now, magnetic fields can be included in this theory quite easily by changing the thermal pressure to a thermal pressure plus magnetic pressure. So this is actually a very simple replacement of parameters here. Any magnetic pressure can simply be included by replacing the Mach number by a Mach number that has a contribution from the magnetic pressure here. This is this plasma beta, just thermal divided by magnetic pressure. And so when we do this, we can just replace the Mach numbers by this factor, and immediately we have magnetic fields included in the theory. So that was simple. And we can now again test it. Here's a simulation without magnetic field on this end, on this side, and then one with a typical magnetic field of 3 microgauss. And you see that here the structures are sharper, so the magnetic field or the magnetic pressure tends to wash out structures. And it also tends to reduce fragmentation, which is a bit counter to what we've heard in the previous talk, where increasing the magnetic field actually led to a decrease in the characteristic mass of the IMF. I would say it should rather increase the characteristic mass because it decreases the amount of fragmentation, which you see here. So the number of objects formed is only 60, whereas here is a little bit more than 100. And the rate is about a factor of 2 different between these two extremes. Okay, of course, those were only 2 simulations, and we have to test the theories with many more because it depends on these 4 basic parameters. And we have actually done some simulations where we vary the mass between 300 and 4 times 10 to the 6 solar masses, covering a wide range of masses, and then different forcing, solenoid mixed compressive, and different Mach numbers from 3 to 50, also typical of molecular clouds in the Milky Way, and different alphane Mach numbers, so different magnetic field. And the agreement here between the theory and the simulation is actually quite good. So this covers 2 orders of magnitude in star formation rates. And the models that are not so consistent are off by less than a factor of 3, but those are relatively low resolution simulations. And we actually see that when we increase the resolution, we nicely converge to this 1-to-1 relation. So that works quite well. But how does this compare to observations? What we can do now, so I showed you this Heidermann et al. Plot of the star formation rate column density versus gas column density in the beginning of the talk. Of course, we have to compare this now and see what we get. And from the simulations, we can use lines of sight along each of the zinc particles, measure the amount of gas in stars at for that line of sight, and then also measure the amount of gas in that column. And each of these dots is actually such a measurement. So each of these is a zinc particle, essentially, for which we can measure both sigma SFR and sigma gas. And to see the distribution of these points better, we can add some contour levels here. So the thin contours actually cover 99% of these dots, whereas the thick ones only 50% of the distribution of the scatter. And because in the simulations we can also control the star formation efficiency just by waiting a bit longer, more gas gets converted into stars, and so we compare these two colors here for star formation efficiency of 1% blue and 10% red, which is in the range of typical star formation efficiencies for molecular clouds in our galaxy. And when we do this, we get this distribution. It has, of course, if you change the star formation efficiency, you simply wind up more gas in stars, and so it has to go up in this direction. Yeah, when more gas gets accreted onto stars, you get less gas and more stars. So the direction must be in this way when you change the star formation efficiency. Now, how does this finally compare now with the observations? So we can add the Heidemann et al. Sample. There's Taurus, then there's YSO measurements in different clouds from the Coast Disk and Gold Belt surveys, and then molecular clumps. And the agreement here is actually quite okay, but it's not perfect. It seems that the simulations slightly overestimate the star formation rate. And this is easy to understand because in these simulations, in these simple simulations I showed you, no feedback was included, which means that the core to star efficiency was 100%. But as I said in the beginning of the talk, this is unrealistic. But we can account for that or correct for that at least simply by saying that this only 50% of what we have here is in the simulations. And when we do that, then the simulations become actually even better consistent with this, with these clouds that are observed. And this leads me to the conclusion. So if there's anything you want to take home from this talk, supersonic magnetized turbulence is really the key for star formation. So it's worth understanding supersonic turbulence. And I've shown you a theoretical model that predicts the star formation rate based on 4 dimensionless basic parameters: the virial parameter, the forcing, the sonic Mach number, and the magnetic field strength. And we've seen there's very good agreement between theory, simulations, and observations. And I would like to end here with a quote from my green little friend, Yoda, and say thank you for your attention.
Thanks very much, Christoph. Are there questions for Christoph? Over here. Please, could you identify yourself when you ask a question?
One question I have is just the relationship between sort of the more abstract forcing that you're using and then more realistic forcing, say, from discrete sources like outflows. Because when you see when Nakamura and Lee, and in our work and Carroll et al., you see that the turbulence actually looks a little different when you actually put in the sources driving it. And so just what you think of that.
Yes, that's absolutely clear. I think we need these experiments where we put in real drivers like you do, or supernovae, and then actually compare this with this idealized, very idealized forcing that I used here and compared, and see how it compares, whether it's more solenoidal or more compressive, what you get when you drive with actual jets, or when you drive with actual supernovae.
There was a question here.
Fabian Heitsch. So my question is, so what happens if the gas is not isothermal anymore? How would that affect your theory? Because, I mean, we heard earlier about temperature variations in molecular clouds, and I assume the density contrast you get in your turbulent models are probably a few orders of magnitude. So how would that affect your models?
I mean, in this particular case, we only look at density ranges that are almost isothermal. So when we look at things like a cloud, they are about here, and then when they form cores, that happens in a phase where the gas is roughly isothermal. So in that sense, it wouldn't change the situation much. But of course, as I said, locally, radiation does important things to the gas. So it reduces fragmentation. So we should, from these simulations I showed you, we should not look at the IMF because we would get that wrong. But the star formation rate, I don't think, is extremely dependent on variations in the temperature.
Sylvie Cabri.
Actually,
I had two questions that are related to the two previous ones. The first one is a naive question, but I'm a bit surprised. How do you explain that the observations are better reproduced with solenoidal compression when you argued initially that all the sources of turbulence should produce compressive modes? And the second point is, do you think that ambipolar diffusion, these are all ideal MHD simulations, I assume?
That's right,
so
yeah.
what would be the effect of ion-neutral friction?
Okay, that's a good question. So the first question was about essentially what has been measured in Kainulainen et al., so this slide, where they find that when we compare the simulations here with different forcing to the observations, then these points here, which are solenoidal and mixed, are sort of comparable here with the nearby star-forming clouds. But if you go to more massive infrared dark clouds, this fraction increases. So it's a good question. I don't know why we still see such low B parameters, even though most of the drivers should actually be more compressive. But on the other hand, if you do this experiment with purely compressive driving and just look at the velocity field, you actually find that you generate a lot of vorticity, a lot of solenoidal motions just by interacting shock fronts. When they collide, you get maybe an impression that looks more solenoidal, even though the driver was originally compressive. And the second part of the question I just forgot, which was ambipolar diffusion, yes. Ambipolar diffusion, difficult to say. Well, I mean, I have this slide about ambipolar diffusion here. I'm not sure we really need that. As Mark pointed out, these clouds are usually observed to be supercritical, so I'm not sure we really need ambipolar diffusion to explain star formation, but it's certainly changing what's happening on small scales, but I wouldn't say it determines star formation.
Hi, Jonathan Tan. So in the last talk by Philippe André, actually, he showed very nice examples of filaments, and at least some of them had very ordered magnetic fields on large scales. I'm curious if in the simulations you see filaments with such ordered fields on both sides and fairly uniform, because that might argue magnetic fields are actually relatively important for even the large scale dynamics.
I actually have a movie, and it might be going a bit in a different direction. So this shows the same simulation with magnetic field, and then with the magnetic field vectors plotted on top of these. And so when you have these dense cores, you actually tend to have very intermittent fields. So they change direction all over the place. But what we do here is we did not put in a mean magnetic field to start with. So we only have such a tangled field to start with. So in principle, what you put in, you get out. So these are magnetic field structures. These are supposed to resemble magnetic field structure inside a molecular cloud. Whereas I think for the very formation of a molecular cloud, it's maybe more important to look at these striations and ordered magnetic fields.
Ralph?
Yeah, so Christoph, just on your solenoidal part of your calculations, in the MHD case, those kind of motions would presumably produce rather strong toroidal fields. And that would alter the theoretical ideas that you have there. It's not just the plasma beta that enters, but the torsional fields. Toroidal fields will squeeze gas in a different kind of a way. Did you see such effects, deviation from the theory?
You're absolutely right. So the simple extension of this theory to include a magnetic field only includes magnetic pressure. It does not include magnetic tension. So that's really a limitation. So we should bear in mind that this only works for alpha and Mach numbers larger than unity. Whereas if you have a really strong ordered magnetic field, this theory does not work anymore, and we have to extend it. But I don't know how at the moment.
So Paul Clark. So Christoph, the observations seem to suggest that the star formation rate correlates quite well with the column density above a certain threshold. Could you say how that fits with what you're showing here? You're showing things you tend to be showing things in terms of density and volume density, not column density here. You're showing stuff with connects to Amanda's stuff, but she's doing something slightly different to what Charlie was doing.
Do you mean, in the comparison to observations, it's all in the observational frame. So we try to process the simulation in a way that an observer would process a map if I gave them.
Right, but this is not what Charlie's doing when he's looking. So I mean, Charlie Ladder, in the Ladder Tau study, that's not what they're doing, right? They're not looking at the Schmidt-Kennecke relationship within a cloud, for example.
That's right. Yeah.
Okay, so how does your results compare with what Charlie's doing?
I can't say in detail because I haven't tried. But of course, what Charlie does is computing an actual mass from the column density, which involves, of course, some geometrical assumptions. And I just didn't want to go through this difficulty here and try to stick with column density or column quantities. Yeah.
Okay, let's thank Christoph again for a very interesting talk.